no. Okay. So hopefully the camera's going to start coming back now. Excellent. All right, is this in screen cam, Kayla?
Yes, but there is something.
Okay, that's fine. All right, so what I want to do is I want to talk a little bit about efficiency and clever ideas. And again, while we are doing this for the Superstar Destroyer, which does not really have much of an impact for the world, the general philosophy of trying to do things well, trying to find clever ideas, has enormous importance. I want to talk about a few interesting things. How many of you are familiar with the US battle for Midway in World War II? All right. Why is Midway so important?
Because it was an important refueling stop to have our planes actually be able to get to Japan.
So strategically it was important for location. Why was the battle important?
Isn't it regarded as like the turning point of the war?
It is regarded as the turning point in the Pacific War. Before then the Japanese had aircraft carrier supremacy. They had far more aircraft carriers than we did. After the battle, we had aircraft carrier supremacy. I believe they lost 4 aircraft carriers, we lost 1. It completely changed the theater of the Pacific War. One of the reasons the US did so well is we actually intercepted Japanese transmissions and we had cracked most of their code and we knew their battle plan. Now, certain US Civil War generals have shown that even knowing the enemy's battle plans, if you're timid, is not enough to win. So you can look up which US Civil War general was too timid to win with Lee's battle plan. The question is, can you trust an intercepted message? Is it really the Japanese plan or is it a trick? During World War II, we tried to mislead the Germans, and successfully, as to where D-Day was going to happen. This was Operation Fortitude. The Germans could not believe that General Patton was in hot water for hitting an enlisted man. He's our best general. You're going to take him out of the command structure because he slapped a person? This is very different than this winter study. Okay? You know, if you need to slap some... Oh, this is being recorded. All right. So the Germans could not believe it, and so the Allies said, you know, we've intercepted a lot of German messages, we've cracked a lot of their codes, let's create a fictional army around Patton and make the Germans believe that we're going to land at Calais. And it was beautifully successful. Hitler kept Panzer tank divisions in strategic reserve, could not believe that the landings would be at Normandy, not at Calais, with Patton in command. For World War II, for the Midway battle, we had intercepted most of the Japanese message and decrypted most of it, but there were parts of it we didn't understand because the Japanese used code designations for different locations. They didn't say Midway. They said, I think, AF-15. And so we thought AF-15 meant Midway, but it could have meant Hawaii, Australia, the Pacific West Coast. And if we guess wrong, and if we commit our forces to the wrong place, we lose. So the US Admiralty decided to go all in. And they decided to believe that they had correctly decoded the messages, and they wanted to be positive that AF-15 meant Midway. Does anybody know how we got confirmation? Yes, Cameron?
They had Midway break a pipe.
Yes. In one of the strangest orders in the history of the military, on a very secure channel, the base at Midway was told to deliberately break one of their water pipes. And then in a routine message, in a either broadcast in the clear or broadcast in a code we knew the Japanese had already cracked, Midway reported, oh, by the way, we have a broken water pump. If we don't get a replacement in 2 weeks, we'll be out of fresh water. Just make sure you give us one in the next reshipment. And then the US later intercepted a message from the Japanese saying AF-15 has a broken water pump and needs a replacement in 2 weeks or they'll be out of fresh water. And it was a beautiful trick to get the Japanese to admit that AF-15 meant Midway. And so, the reason I want to bring this up is sometimes the most important contributions are very elementary. They're not using the most difficult mathematics, the most advanced mathematics. A lot of people look down on certain parts of mathematics because, oh, you're just using high school algebra. Sure. Baseball is a multi-billion-dollar business a year. If you can use high school algebra and find a better way, a better statistic of looking at things, elementary statistics, elementary regression, go for it. And so this is one of the reasons why I want you to just bring something like this on your radar screen. The next thing I want to mention today in terms of just efficiency is who knows what QWERTY stands for, or why QWERTY is a key word?
It's the layout of most keyboards.
It's the layout on most keyboards. Why do we have QWERTY keyboards?
Because it's
Yes. Does anybody here still use a typewriter? Right. And so we're stuck with this. All right, the Dvorak keyboard is much better, but in the old typewriters, when you hit, the keys would lock. And in order to prevent this from happening, they deliberately designed an inefficient keyboard to slow you down and to make you alternate between hands. If we truly loved you, if your parents truly loved you, they would have made the effort to switch keyboards. If I truly loved my kids, I would argue more strenuous. Okay, I love my kids. Please, everybody, let's learn Dvorak. We're stuck with it. So it's very interesting seeing which things end up getting a life of their own. When you do something and it becomes institutionalized, it's very hard to break. It's worthwhile every now and then to go back and think, why are we doing things this way? There's a reason we're spending a couple of weeks playing with Legos. We do enjoy it, but there's a lot of good lessons to learn from this. Look at how things are being done. Always be questioning, why are we doing it this way? These instructions were written linearly. They were written for a couple of kids or a father with his 2 kids to make a superstar destroyer step by step by step by step. It's a lot of fun. We had a great time doing this. But we're doing a very different task now. And because we're doing a different task, you want to be able to look at things with a fresh perspective and break free from that. All right, the last thing is just I want to have some serious math content for today. I want to talk a little bit about Pascal's triangle. How many of you have seen Pascal's triangle? All right, hopefully the camera's still catching me. So it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And you get each number by adding the 2 numbers to the left and right above, with all ones going along the sides. So the number in the nth row in the kth spot is n choose k, which is n factorial over k factorial, n minus k factorial. If n and k are large, this takes a long time to compute. And so the question becomes, what are fast ways to compute something like this? So again, one of the themes of this class is trying to find efficient, fast ways to do things. There's lots of different ways of doing this. I like to do math with my kids, not surprisingly. And a couple of years ago, Cameron and I were looking at Pascal's triangle. And there's a lot of interesting patterns. Do you remember how we get the interesting pattern, Cam? How do we look at these numbers? We check to see if they're not prime, odd. So if they're odd, we fill them in, and if they're even, we erase. So we erase the 2. And patterns start to emerge. Now, to really see the pattern, you want to go down a little bit further. So I wrote a computer program with slight assistance from my son. And so what I'm going to do is I'm going to play the clip right now. Hopefully it's in view. And it's adding rows. I've just rotated the triangle 90 degrees. I'm also rescaling it so that at every moment, all the rows are rescaled, so I'm going the same distance over here so it fills the screen. It's the Sierpinski triangle. There's a fractal structure to Pascal's triangle. All right? I could not find a clip of this on YouTube, which was disappointing. So I've written this and I've posted this. This is the only clip I know that's actually constructing Pascal's triangle row by row by row and seeing the structure emerge. If you want some more math content to this, try to prove rigorously that you're going to get Sierpinski's triangle. That every time you get something like this, when you go to the next level, the pattern's going to repeat. Every now and then you get a row that's all odd. All right, let's see. Cameron, odd plus odd is?
Even.
So once we have 2 odds, when we add them together, we're going to get even. What's even plus even?
Even.
So the even pattern is going to persist. We have the one that's odd, so we have all these even numbers now, and it's going to be filling in, it's going to be getting smaller and smaller. You can try to prove that you have a pattern like this. So fractal structures are structures with self-similarity. We talked a little bit about this with Horner's algorithm, Star Trek II, The Wrath of Khan, making figures like this. The question is, how do you do something like this very quickly? Right now, there's a lot more dots. It's reading this in from a file, so it's not computing things. To make it go a little faster, the camera I know will get off me, I'll just speed it up a little bit. And hopefully that'll do a little bit better. And then eventually it'll crash, but. So the question is, what's a good way to calculate Pascal's triangle? If you really want to do this super efficiently with computer science, because we have so much self-similarity, once we have certain values, you can use that in to almost recursively fill in the structure. I'm not using that information, I'm actually recomputing things. There's a bunch of different strategies you can do. If you know a row, you can start calculating the next row from the previous row. And so one way to calculate Pascal's triangle is calculate it row by row, keep one row in memory, and then use that row to get the next. When you do that, you only have to store a row whether or not the entry is even or odd, 0 or 1. So in terms of what you have to store, it's not so bad. There's other methods you can do. Yes?
The row be growing larger though?
The row will be getting larger. And you can see in the beginning it whips through it very quickly in terms of drawing it. As you have more and more dots that it's putting in, it's causing it a little bit more trouble in terms of just how Mathematica deals with the image. I don't care enough about this class to do Mathematica automatically, dynamically reallocating processing time for displaying this. So if you know what the rows are, you can get the next row without too much trouble. You can actually jump ahead to a certain row, calculate it, and then start moving from that point onward. The advantage of this is you don't have to compute everything up to a point. If I want to know Pascal's triangle from here on mod 2, I can just calculate this row and then move on. I don't need that stuff. If I really want to use CS and recursion, I can of course reduce it to the stuff here. One last trick I'll just mention is, let's say I want to just calculate what's going on from the row 2015, a completely non-random number. Okay? If I want to get 2015 and just start there, one possibility is to start in the beginning and compute, and then just throw away all that computation. That's very wasteful because I'm computing things I don't care about. Is there a way to just jump to row 2015 without doing all the stuff beforehand? Yes?
Well, so you know the first and last two digits of row 2015.
Correct.
So you know the first digit is going to be a 1.
Mm-hmm.
And then the second digit, well, are we counting the top as row 0? Or
Doesn't matter.
Well,
So,
well, then you know that the decimal then would be 2014 still.
right, but then the formulas start getting more and more involved. The idea is you don't want to compute n choose k at each time. What you want to do is you want to notice, am I in focus at all? No. All right. What you want to do is you want to notice that if you can compute one element, you know n choose k there. You then want to figure out what's n plus, yeah, I'll hopefully get back. I feel like Darth Vader with this coming up. So let's say we know n choose k. The next thing we want is n choose k plus 1. We want the very next term. Well, this is n factorial over k factorial n minus k factorial. This is n factorial over k plus 1 factorial n minus k minus 1 factorial. How should I rewrite k plus 1 factorial?
K factorial times k plus 1.
Excellent. So in fact, if I do a little bit of algebra, I get n minus k over k plus 1, n factorial over k factorial, n minus k factorial. I needed an extra n minus k down below. I put up here. I've done one of my favorite things in the world. I've multiplied by 1. If I multiply by 1, I don't change things. The other thing I love to do is add 0. All right. So what we've noticed is we get that this is just equal to n minus k over k plus 1 times n choose k. So if you know n choose k, you can get the next term very easily from it by multiplying like this. Should we multiply first and then divide, or divide and then multiply? It matters. Excellent. Why do we multiply and then divide? We do not want decimals. And so the binomial coefficients are always integers. If I divide first, there's a danger that I get a fraction. There's a danger I could have round-off errors and whatnot. If I multiply first and then divide, I will be OK. And this allows us to march down, and it keeps the computations very manageable. All right, so this is just a quick, short introduction to some of the mathematics for today. I will be interested to see what Cam and Kayla do in their math today.